So thank you all for still being here for the very last talk of this workshop. And this is a joint work with Chihao. He's also here. He's graduating this year. And this talk is about the tractability of a class of counting problems on a class of graphs. So an important class of counting problems are spin systems. And in a spin system, we are given a graph, and each vertex is a variable, taking values from q possible colors or states. And each edge is a binary constraint. So the weight of a configuration is given by this product. And the partition function is this total weights of all configurations. So this talk is about Holland problems. The Holland problem is an edge spin model. So each edge is a variable, and each vertex is a constraint. And the Holland is this sum of product. So now each constraint function, also called a signature, may be defined on a very large number of variables if your graph has unbounded degree. And also, the size of the configuration space is a lot bigger. It's q to the number of edges. In fact, a spin system, it is well known that a spin system can be represented as Holland in incidence graph with equality signature on the vertex side and the binary constraint on the other side. In this way, Holland can simulate any CSPs. And so this is counting matchings. It's a typical Holland problem. So with signature at most 1 function, it's 1, 1, or 0. So remember that for symmetric functions with Boolean domain, we can represent a signature as this. So fi gives a function value of input with precisely I ones. So this is counting perfect matchings. The signature is the exact 1 function. And this is counting edge covers. The signature is at least 1 function, 0 or 1. And this is the subgraphs world problem from Jerome Sinclair's Markov chain for ferromagnetic Ising model. And I omitted the edge weight here. So the signature is this parity function. Depending on the parity of the input, the signature returns either value 1 or value omega, or value mu. So let's see. I thought you must be already very tired at this point, so I made this talk very easy. So you have equality, which is like this, okay, and you have matching, which is like this. Perfect matching, edge cover, this is the parity, okay, which is like A, B, A, B. And the last one is counting Eulerian orientation. So in the incidence graph, with this disequality signature, it enforces that your configuration must be an orientation of edges. And on this side, this signature, I call it Eulerian signature. It accepts the input with equal number of 0s and 1s. So use another color. This is Eulerian. this last signature is fundamentally different from all the others. So can you tell why? I'll tell you. Because these signatures, although with unbounded degree, they all can be they can be computed by a fixed by a finite state automaton, right? Sitting at the vertex, revealing the state of edge one by one, but not this last one. So the motivation of this project is that it seems like Holland problems are not just more expressive than spin systems. They're supposed to be more difficult to compute in general than spin systems. And we want to give a class of nice Holland problems which are not so harder than spin systems. But what do we mean by being more difficult to compute? So they are both number P complete, right? So before going there, I want to mention this notion of treewidth. So the treewidth is a parameter, a structural parameter of graphs, which measures how much a graph is like a tree. So the treewidth of a tree is 1, and the treewidth of clique is -1. So remember that the classic algorithms like belief propagation work very well on trees. So yeah, it's natural to consider graphs which are like trees. And indeed, by Crocel's theorem in logic, spin systems are fixed parameter tractable in treewidth. And the actual running time achieved by the junction tree belief propagation in artificial intelligence is exponential of treewidth. That's for spin. And for Holland, if your graph has bounded maximum degree, then the same time bound is achieved in the context of tensor networks in quantum computing. So let me briefly explain why bounded treewidth helps counting. Okay. So usually such algorithms are dynamic programming on tree decomposition. But I don't want to go into detail about tree decompositions and normal forms. I prefer to use another kind of graph decomposition here, which is less popular but more intuitive to me. I call this separator decomposition. Given the graph, the separator decomposition of that graph is a binary tree where every tree node is corresponding to a vertex set, and with the root corresponding to the entire vertex set V, and for a node corresponding to vertex set Vi, it has a vertex separator Si. So Vi is separated into disconnected vertex sets Vj and Vk, which corresponding to its children. And we recursively do that until in the leaves, the sets are empty. The width of this decomposition is the maximum size of the separator, the vertex separator, also the vertex boundary of each vertex set. Okay? And the optimal width of this decomposition is the width of the optimal such decomposition of a graph, denoted as SW of graph of G. So imagine if your graph is already a tree, right? Then the separator should be the root. And every node in the decomposition is a subtree or a subforest, right? So the decomposition of this thing the width of this decomposition is exactly 1 because it's a tree. Okay. It's quite standard to prove that the width, this notion of width, is asymptotically equal to the tree width, and also constructing optimal decomposition is fixed parameter tractable in tree width. Okay, so now with this kind of decomposition, it's almost immediate to get a dynamic programming algorithm for computing the partition function of spin systems. So given any vertex set Vi, we can recursively compute the partition function of the subgraph induced by this vertex set with an arbitrary boundary condition by enumerating all the possible configurations at the separator. And then taking the product of these 3 parts, the partition function of the left child, the partition function of the right child, and the contribution of the separator itself. And this third part can be evaluated directly on site because every spin here is fixed. And these 2 things are just a recursive quantity. So this is actually a tree recursion, a computation tree on the decomposition of graph. And the product here is due to the same conditional independence property of spin system, where conditioning the separator being fixed, the disconnected components are independent of each other. And the tree width gives upper bound on the size of the separator as well as the size of the boundary. So with small tree width, this enumeration is efficient, and also this recursion can be implemented as efficient dynamical programming. So that explains why tree width helps counting in models with such local Markovian properties like spin system. So for Holland, if now edges are variables, and so we can enumerate edge states, and also here is the edge boundary. So if your graph has bounded degree, it's fine because that won't change your time complexity too much. But for general graph with unbounded degree, for general Holland problems, it's very challenging. It's very hard to do that. Actually, just think about for general CSPs, even if you know your graph is already a tree, on tree, how to come up with a belief propagation or tree recursion without enumerating exponentially many local configurations. We don't know how to do that, right? So yeah. So general CSP or Holland can be very different from spin. So back to our goal of classifying the computational complexity of Holland problems according to the graph family and the signature family. We gave a class of nice Holland problems, which are close to spin systems in computation, in the sense that so these Holland problems can be computed in time exponential of n. N is the number of vertices instead of edges. And also, these Holland problems are fixed parameter tractable in tree width. These 2 are closely connected. And this exponential of tree width time bound is crucial because it has certain implications in approximate counting in planar graphs. So let me formally describe this characterization of nice Holland problems like these ones. So So for now, we just assume our signature is a symmetric function. For any partial assignment, we can pin this function with this partial assignment, which means we fix the values of these variables according to this partial assignment tau. This gives us our new function, right? New k-array function. Also symmetric function. So there are many ways to pin this function. It's possible that many partial assignments produce the same k-array function. Think about this function is a parity function. So for any fixed k, it only gives us two functions, depending on the parity of the partial assignment. So that defines a natural equivalent classes between partial inputs. I call it peering. So the number of such equivalent classes gives a natural measure of the dimensionality, intrinsic dimensionality of symmetric function. So for parity function, it's just 2. So this leads us to the key concept of our project. So for symmetric function f, we call f R regular if for any k, the number of satisfiable k-array functions produced by pinning f is at most R. Okay, so yeah, so no matter how once we fix the k, no matter how we pinning those positions, those variables, the number of different functions it gives us is at most k, at most R. Sorry. So for symmetric function with Boolean domain, with this signature form, suppose the partial assignment has I1s and J0s, and pinning this function with this partial assignment, delete I entries from left and J entries from right. It gives us this subinterval as our new function. Actually, every pinning it gives us a subinterval. So being R regular means once we fix k, the number of different patterns of this sliding window of length k is at most R. So with this definition, it's quite easy to check all these functions are finitely regular. Only 2 regular, actually. And not this Eulerian signature. Even though it's very, very simple, almost always unsatisfiable. So yeah, it's quite amazing. The regularity of this Eulerian signature depends on the degree. So that, and for symmetric function of general domain, like domain 3, the signature is simplex, and so this subinterval becomes our sub-simplex, a smaller simplex. And so being R regular means with this smaller simplex fixed, size fixed, no matter how we move around, and the number of different patterns we can get is at most R. So with bounded degree, we always get finite regularity. So bounded degree is just a special case of this regularity. Then we show that for Holland problems defined by R regular symmetric signatures, they can be computed in time R to the ON. N is a number of vertices. And also they are fixed parameter tractable in Treewidth and in R. Yeah. So it means for constant R, these Holland problems are like spin systems, right? With finite state signatures. They are like spin systems. So in our previous work, this base of the time bound was 2 to the r, and now we improve it exponentially to r, and we believe this is essentially tight in general, assuming the exponential time hypothesis. And we extend this result to asymmetric signatures. But for asymmetric signatures with unbounded degree, we must be careful because it can be uncomputable. So we make certain assumptions about that. And also, this result has implications in approximate counting on planar graphs. And in particular, it gives p-test for log partition function and f-p-test for the partition function, assuming the decay of correlation, both on planar graphs. Okay. So let me first talk about this simple exponential time algorithm. It's very, very simple. Given a Holland instance, we assume an arbitrary ordering of vertices. We pick the very last vertex. We enumerate all possible configurations on the edge, on its incident edge, and this gives us a simple recursion for the Holland, right? And the new Holland instances are defined on the graph with n-1 vertices, with new signatures obtained from pinning the old signatures. And by the regularity, we know that at each vertex, the number of different possible signatures is bounded by R. And that's also recursive. So that holds recursively. We need to prove that, but that's true. So yeah, this immediately gave us this dynamic programming because we can memorize all the Holland instance with this dynamic programming table of this size, and it gives us this running time. So it's very simple. And for specific Holland problems like permanent, the running time can be further optimized because we only enumerate feasible configurations, and for permanent, the graph is bipartite. We can use that. So actually, this very simple combinatorial algorithm gives can compute the permanent in permanent of n by n matrix in time n square times 2 to the n, which is very close to the running time of the Reiser's formula, which is n times 2 to the n. And yeah, without using inversion technique. And yeah, so to make this algorithm works for general family of symmetric functions, we need to do some formal works, because we know for each vertex, once we fix the arity, the number of different signatures is bounded, but we still need to be able to efficiently enumerate those signatures by a succinct representation, and also we need to evaluate and further pinning those signatures by referring to the succinct representations. Those are functionalities are called oracles, and they can be realized by efficient data structures for all symmetric functions. But for specific, for Holland with specific signatures, all these things are implicit. So yeah, it's very simple. And next we move on to this fixed parameter tractable algorithm for Holland on graphs with bounded treewidth. Remember that we have this decomposition of graphs that recursively separate vertex set into smaller disconnected vertex sets Vj and Vk, disconnected by this vertex separator Si. And the size of the separator and also the vertex boundary is bounded, upper bounded by treewidth. So here the idea of the algorithm is still similar, that we just enumerate all possible cases within this separator. But now it's tricky because for Holland, edges are variables. And also for vertex in the middle in this separator, it can be adjacent to unboundedly many edges. So how do we do that? But something is still finite. Here, for each vertex in the middle, although it may adjacent to unboundedly many edges, those edges belong to only three groups. Edges adjacent to the left, edges adjacent to the right component, and edges within the separators, within the separator. And remember that we have this notion of equivalent classes for partial inputs. And an observation is that the function value can be fully determined by the equivalent classes of the partial input. Imagine this is still the parity function. Once we know the parity of the three parts, the function value is determined. And the parity of those three parts are just the equivalent classes for the actual configurations of those parts. So now you know what we should do, right? So for each vertex in the middle, in the separator, instead of enumerating all possible configurations, local configurations of its adjacent edges, we enumerate the equivalent classes for three groups of its edges. So for parity function, it's only 8 possibility. And before, by enumerating the actual configuration, these configuration becomes boundary conditions for the new instances, inherited by the new instance. Now, because what we enumerate are not configuration anymore, they are equivalent classes anymore. They are equivalent classes. So now those are not boundary conditions, but boundary signatures. So we represent the equivalent classes as a Boolean signature. I call it peering of function f. So this signature just accept only those configurations fall into the equivalent classes it enforces. Like if it's odd, even, odd, then this one just always accept the odd configurations. Okay, so and it's important to say that by this translation of signatures, the regularity never increases. It never ruins the regularity. So now we have this tree recursion for Holland, and for each vertex in the middle, it enumerates equivalent classes of the three group of adjacent edges, and just send it to the children, inherited by the children in the new instance, and as boundary signatures. And this third part, is Holland defined on this separator. And when we enumerate configurations, this part is easy to solve. This trivial, it's just a product. But now it's non-trivial because those are not configurations. Those are signatures. So it's a non-trivial Holland problem defined on the separator. But the good thing is we know that the size of the instance is bounded by Treewidth. So we can apply our first algorithm, which compute the Holland in exponential time, exponential to the Treewidth. So R to the Treewidth. And we know all those peering signatures are still R regular. So altogether, it gives us dynamical programming running in time r to the order of Treewidth times n, which is the size of the decomposition. So, okay, that's it. So we still need to do these formal works to guarantee those, functionalities. Those oracles are efficient. Now we have a new oracle, which is peering oracle. Translate a signature to these Boolean signatures, and we need to do some extra work to make sure that recursively do these translations will not make the number of signatures explode. And and that's true. And they can be efficiently implemented by data structures for all symmetric signatures. So we have this theorem, which says basically for regular, for Holland problem defined by this finite state signatures, they are like spin systems. But that's only for symmetric. For now, that's only for symmetric signature. For asymmetric signature, pinning, we can still pin the function, right? But pinning must specify the locations, the position of pinning. And we can similarly define the notion of R regularity. So a function, an asymmetric function is R regular if no matter how we fix the position of pinning, we fix the positions first, then no matter how we fix them, once we fix those locations, no matter how we pin those variables, the number of functions it produces is bounded by R. Okay, so for each fixed set of positions, no matter how we pin them, the number of functions is bounded. So with this definition, all these results can be extended to asymmetric signatures with the same time bound, but assuming the availability of those oracles. So for symmetric signatures, we can just implement those oracles explicitly. But for asymmetric functions with unbounded degree, even evaluating those functions can be undecidable. So, but we believe that for sparse family of efficiently computable functions, make such assumptions not so crazy. So, okay. So this result has certain some implications in approximate counting on planar graphs. So for planar graph, we know by Baker's decomposition technique, a planar graph can be decomposed into a sequence of subgraphs with bounded treewidth. And it was discovered by Jeremy Goldberg, McQuillan, that with Baker's decomposition, if we have a subroutine to compute the Holland in time exponential to the treewidth, then for classes of Holland on planar graphs, if the Holland is always exponentially large, then we have a Peters for the log of Holland. So for spin system, it's just a log partition function. It's a very interesting quantity by itself, and so it means that the strong hardness result of SLI cannot hold anymore on planar graphs. So this gives a separation between the computational complexity of approximate counting planar graphs and on general graphs. So it's a very interesting phenomenon. Once we have planar structures, we cannot have such a strong concentration. And then with correlation decay, with strong spatial mixing, assuming the strong spatial mixing, which basically says you can ignore any information beyond the log n ball to give a, so the information within the log n ball is sufficient to approximate this marginal probability. Okay, it's a information. It's a sufficiency of local information. It's not an algorithm. But for planar graphs, we know that the Treewidth of log n ball is linear of log n. So with the subroutine which can compute which can do the exact counting within time, exponential of Treewidth, this gives us our polynomial time approximation algorithm for the marginal probability. And for self-reducible problems, this gives our F-pitas for the Holland. So let's wrap up. So we locate a class of nice Holland problems that behave like bounded degree number CSP, like spin systems. In this sense, they have time complexity, this kind of time complexity. And this notion of regularity implies efficient dynamic programming algorithms. But it's not preserved by holographic transformation. We still don't understand what holographic transformation does to this finite state signature. And also, it does not cover many other exact counting techniques like inversion-based techniques, a principle of inclusion, exclusion. But we saw that it can achieve something similar. It could be some intrinsic connection there. So, and an open problem is whether this is tight. We believe this is tight. We believe that this regularity can goes up to n. So we believe there should be such lower bound. There should be Holland problem, which is easy for decision, hard for counting, with Boolean symmetric signature that has such n to the Treewidth lower bound, assuming the exponential time hypothesis. So far, there's no such lower bound. So far, the fine-grained lower bound, I guess it's only 2 to the Treewidth, the most for problem which is easy for decision. So, and by our discovery, such problem must have unbounded degree signature and must be irregular. So this Eulerian orientation is nice candy. So yeah, that's it. Thank you.
Do you think you could do anything at all similar for other graph width parameters? In particular for bounded clique width, there are some cases which seem like they should be tractable but aren't known to be. There's only sub-exponential algorithms known.
Yeah, I think definitely there should be something there. But we're not experts on actually structural graph theory. So we can do something, something very concrete, but not that generic. So yeah, but I guess there should be something there for clique width. Yeah. But for counting, it seems like Treewidth is somehow very natural. Yeah. For clique width, it's difficult to work with. Yeah.
I have 2 remarks. One to this question. Clique width doesn't seem to function because already for the chromatic polynomial or the top polynomial, clique width doesn't have so much to compute it much faster.
I see.
The other thing is that I think when you quote Courcell's theorem of 1990, he only deals with decision problems and optimization problems. If you want to do graph parameters, it's a later paper he wrote with me,
Oh.
which deals with parameters. Kursel, Markowski wrote it. So when you quote it, you should quote the right way.
Okay, so yeah, we will make this correct. Sorry, yeah.
Anybody else? Okay, so I want to thank Yitong, but also the organizers of this nice workshop and the program and the science.